Swayam Prabha. Digital India. Educated India.
Now, second thing that we need to note is this. If arm A has been pulled more than U bar TA times, right, then the width of its confidence bound is going to be small. So remember when we say UCB, right, it's the empirical mean plus square root of 1 divided by, or rather 2 divided by the number of pulls times log t. Right? If the number of pulls is large, so that what's inside the square root is going to become small, right? So more concretely, since x is at least U bar TA, right? I mean, you can it follows that square root of 2 over x log t must be less than or equal to square root of 2 over x U bar TA log t. And if you fill in now for U bar TA from what we had specified, right, you'll notice that this whole thing is at most capital delta A over 2. Okay, so this is actually the reason U bar TA had to be set to that particular quantity. Why? In order that this LHS would now be less than or equal to delta A over 2. Okay, why delta A over 2, right? So if this UCB, right, so rather the confidence width of arm A is at most delta A over 2, right, and this event has happened, that the UCB of arm A has exceeded P star, then what it means is the empirical mean of arm A must be at least delta A over 2 higher than its true mean. Okay, so for a second, forget about the math and just imagine this visually. Okay, so there is the actual empirical mean and the actual true mean of arm A, which is PA, and the actual true mean of arm star, which is P star. Okay, if the UCB of the suboptimal arm has exceeded P star, and on top of it, the confidence width, right, as a part of that UCB is only half of delta. It's not more than half of delta. Remember, delta is actually the difference between the optimal mean and the arm's mean. So if the width is only less than half of delta, the only way the UCB can exceed P star is if the empirical mean of arm A is itself more than half the way, right, which is basically PA plus delta over 2. So this is not like a probabilistic event or something like that. This is just like a mathematical argument. Okay, and this is happening by virtue of the fact that arm A got pulled a sufficient number of times, and that sufficient number is U bar capital TA. Okay, all right. So we what did we have on the previous slide in 4.1? We were looking at the probability that the UCB of arm A exceeds the UCB of arm star. We broke that down into saying, well, if that happens, one of these two things must happen. The UCB of arm A exceeds P star, or the UCB of arm star, right, falls below P star. Further, if we just now zero in on the first of these events, the additional fact that arm A has been sampled many times, right, means that the confidence width is small. And therefore, if this UCB is exceeding P star, the empirical mean itself must exceed PA plus delta A over 2. Okay, all right. So now we go to step 4.3, which is going to combine what was going on in 4.1 and the two things that we showed in 4.2. Okay, so in 4.1, right, we replaced the random variables by a sum that went over constants. So this is basically just the statement of 4.1. Okay, and now one step at a time we can bring in what we did in step 4.2. Okay, so one of the things that we showed in 4.2 is if this event happens, right, then the UCB of arm A must exceed P star. That in turn implied that the empirical mean of arm A must exceed PA plus delta A over 2. Okay, we've actually done two steps because this was one of the things that was implied. The other thing is that we've left it as it is. The fact that arm star's UCB, right, falls below P star. Now that can be sort of written in a slightly different way. See, P star plus square root, right? That's the UCB. And if that falls, P hat star plus this square root term is the UCB. So we've just taken the square root term and put it on the right hand side, okay, and said the empirical mean must be less than P star minus the square root term. Okay, so now finally, after doing all this, we are in a position to directly apply Hubbing's inequality. Okay, so does this look familiar? What is the probability that the empirical mean exceeds the true mean plus something? Right. Similarly, what's the probability that the empirical mean falls below the true mean minus something? So these are both tailor-made for Hubbing's inequality, and we can precisely upper bound this probability by e to the minus 2x delta I over 2 the whole squared, 2u epsilon squared. And similarly, for the second term, now you do the simplification, things will sort of cancel out, and you will see that each of these can be upper bounded by e to the minus 4 times log t, okay, which is the same as 1 over t to the 4th. And so if you add these two things up, you get 2 over t to the 4th. And if you're summing up 2 over t to the 4th, and there's two sums that go from something to t, right? You multiply them out, at most you can have like a t squared over there. So, I'm saying this, I don't know, in a few seconds, but it'll take you maybe a minute to convince yourself for each of these steps, right? And then another revisit of the whole thing to convince yourself in aggregate about what's going on. But this is going to be sum of basically 2 over t squared, okay, going from little t, going from 0 through capital T minus 1. Be generous, make the capital T minus 1 infinity instead, okay, because we are going in the direction of upper bounding things. And this is a sum that is known, okay, in mathematics. If you sum up 1 over t squared, you'll get pi squared over 6, okay. So that gets multiplied by 2, but at the end of it, right, we have shown that, by the way, this pi here is pi, okay, 3.14159, whatever. Right, so we've shown that b is upper bounded by a constant at the end of all of this. Okay, so what does it mean? It actually means we are done. Okay, let's not lose the wood for the trees. Of course, these are all the trees and the shrubs and the foliage, but what is the wood, right? What really did we do to get to this? So let me summarize, okay? Take some time to assimilate and to digest. Here is what we did in the proof. Okay, we said we want to upper bound the regret, but then for that, it suffices for us to upper bound the number of pulls of each suboptimal arm A. Okay, this is what we did in step 1. And thereafter, we said we will split these suboptimal pulls into two regimes for free, right? Let's just give each suboptimal arm U bar capital TA pulls. Okay, earlier it might have seemed like this U bar TA was coming from nowhere. Where did we come up with this particular quantity? But then later in the proof, right, you saw that if an arm has been pulled U bar TA times, then its confidence width has shrunk, right, to less than delta A over 2. That is useful, right, because if an arm is being pulled in terms, in spite of a confidence width that is only delta A over 2, then it must have deviated a fair bit from its true mean, right? And that we can upper bound by Hubbing's inequality. Well, of course, the arm might have deviated. The other thing might have happened is that the optimal arm might have fallen substantially down. That also can be bounded using Hubbing's inequality. Okay, the probabilities are small enough, right? This is the reason UCB was doing 2 divided by U log t. Why did we do 2 divided by U log t? Because then we would get 1 over t to the 4th, right, inside of that summation, and then that sort of gets multiplied out by a couple of sums, and finally we're left with a constant. Okay, so after each arm has been pulled U bar 80 times, it will be pulled at most a constant number of times. In fact, the constant is very small, right? Pi squared divided by 3 is what, 3 or 4 or something like that. Okay, so basically you'll get pulled U bar 80 times. Okay, and that gives us the bound. Now, I'm not going to do the bound for KLUCB, but the proof is basically the same. You'll have to be a little bit more careful in a few places. So one is, as you probably already guessed, rather than using Hubling's inequality and inverting it, we can use the tighter KL inequality, which we also covered at the beginning of class. And the second thing, right, we had the step of converting the random variable, upper bounding that, right, by a sum of probabilities over constants. Now, we did it in a relatively naive way. We didn't really bother so much because we really wanted sort of the order dependence to be in terms of log t, which is what we got. But you can sort of do it slightly differently. Okay, it gets a little bit more sophisticated, not something that we will cover here. So instead of doing what we did, right, which is called like naive union bound, you can have a slightly more sophisticated argument for converting the random variable to a constant. Okay, so that's what's done as a part of KL UCB. Therefore, the bound is tighter, and we know that it actually matches the bound of Lai and Robbins. Okay, so there. So I'm done with section 2 of this lecture. You are not done with it. Okay, so I fully realize that this is fairly complicated stuff. So if it helps, right, please also look at the proof in the original paper. That's going to be a lot more succinct than what I have demonstrated to you. But go back and forth a little bit. If you have questions, you can ask me. Okay, so that's UCB anyway. And what's coming up next is Thompson sampling. Not a full proof, but some sort of understanding of how this method works. Well, so you're familiar with Thomson sampling, which was given to you as an algorithm. So you sort of know the syntax. What you don't know is the semantics, right? In the sense, what is the thinking, right, behind this algorithm? That's what we will describe. Just briefly, what was the algorithm itself? We're going to count for each arm the number of successes S and the number of failures F in every instant of time. We're assuming the rewards are 0 and 1 over here, and maintaining this beta distribution as a belief over the unknown true mean TA. So it might look like this for each arm at some point of time. And then what do? We draw a sample XTA for arm A from its corresponding belief distribution. And whichever arm has the highest XTA value, right, we go and actually pull, which means we'll get one more success or failure, and that will be as some indication of the true value of PA. Okay, so this you're familiar with. Now, what is the way to think about Thompson sampling? Right. So the basis is what is called Bayesian inference. Okay. So you've probably seen this in some form when you did a probability course or some other machine learning course. But what I put up here is basically Bayes' rule. Okay, something that you're probably familiar with. So if you have two events A and B, then the probability of A given B, right, can be written down as probability of B given A times probability of A divided by P of B. Well, the easy way to rationalize this is if you take this P of B and put it on the LHS, then both of these are basically the probability of A and B, right? So you've just taken it out from one side and made it the denominator of the other. Now, how are we going to apply Bayes' rule? Here's what we're going to do, okay? So, we are interacting with an unknown world. Okay, so let's say there is a world, W. There's a set of all possible worlds, capital W. But there is one particular world amongst those, which is the reality, okay, which is the one in which we live. Except we don't know what that world is. Okay, and the idea is, with time, right, as we see how this world generates evidence, we'll be able to get a better and better estimate of what world we might actually be living in. So let's make this idea a little bit more precise. Okay, so in the absence of not knowing what the world is, what we do is we maintain a belief over possible worlds. Okay, so initially this suffix here of belief, right, says it's like time. So initially, right, at time 0, we don't know anything. So we can have any arbitrary prior belief on the set of possible worlds, right, probability with which they occur. So by the way, when I say world over here, sometimes it's also called a hypothesis. Okay, there's a whole universe of hypotheses. We don't know which is the correct one, but as the hypotheses generate evidence, we can slowly sort of hone our belief to try and identify the ones that are more likely. Okay, so we have a belief distribution over possible worlds. Now, worlds produce evidence. Okay, so what we're going to assume is that if there is a particular world W, the process by which the world produces evidence, that is something that we know. It can be a random process, but it is something that we know. In some sense, we know what is the probability of E given W, and we're going to go over time. Okay, so after, let's say, m time steps, the world would have produced E1, E2, E3, E4, EM. You can make different assumptions about this, but for this illustration, let's just assume that these things have happened independently. Okay, so there is a world, it produced evidence E1, then again it produced evidence E2, again it produced evidence E3, which of course are all things that we see, but there's really no dependence in this process. Okay, these are IID samples drawn from probability of E given W. Right? But then notice that these E's are telling us something about the world. So what we really want to do is to refine our belief based on evidence. Okay, so belief 0 was our belief distribution over W without seeing any evidence. So belief M, right, after M steps, is the probability distribution over W having seen evidence E1 through EM. What is the probability of W given all of these things that we have seen? Okay, now the hope is that we will be able to sort of efficiently maintain this belief distribution, belief M. And how do we do that? We do that by using the laws of probability and basically Bayes rule. Okay, but one thing to notice, right, to emphasize to you is, it is not that in reality there are multiple worlds coming from some probability, right? There is actually one world. Okay, so when you're playing, when you were playing that game that we played on the very first day, there are 3 fixed coins and they have 3 fixed biases, right? Those biases are like the worlds that we are talking about here. But we don't know what they are, right? So this belief distribution is something that is there in our mind. We are choosing to use Bayes' rule to refine our belief distributions because that seems to be a reasonable thing to do. Okay? So precisely how we go from your belief distribution at stage M, right, after M bits of evidence, to belief at M plus 1 is what's given on this slide, which probably looks a little bit forbidding with so much math going on, but I mean, most of this you know, all right? So let's just do it one step at a time. I think you'll be able to follow. So the point, by the way, point of this derivation is to give, right, an efficient procedure to calculate belief M plus 1. It turns out, as you see from the last line, that really all we need for that is belief at stage M plus the evidence that happened at M plus 1, right? So the belief distribution at stage M is really sufficient to describe everything that happened before. You don't have anything here that depends on M minus 1 or M minus 2. So it's called a sufficient statistic sometimes. So let's just do this. So the first line is just the definition. Belief M plus 1 of W is the probability distribution over W given evidence E1 through EM plus 1. So again, the use of comma means it's like a conjunction. Okay, this is E1 and E2 through EM plus 1. Use Bayes rule and write this as probability of E's given W times probability of W divided by the probability of the E's 1 through N plus 1. Now, we use the fact that the E's were generated conditionally independently, right? That when we fixed W, the E's were given drawn IID. So therefore, we can write probability of E1 through EM plus 1 given W as probability of E1 through EM given W times probability of EM plus 1 given W. Okay, this is going to make life convenient for us. The other things were left as they are. So going from this step to this step, what we are doing, we take the probability of W at the end of the numerator and then combine it with the first term in the numerator and see that this is just a big conjunction, right? It's a probability of E1 through EM and W, which now we can rewrite as probability of W given E1 through EM times probability of E1 through EM, and we leave, just carry over from the previous step, the probability of EM plus 1 given W. Okay, so now we have to, we are actually in a position to collapse some of these things into a form that we want. But just pay attention to one detail. So probability of W given E1 through EM is basically the definition of belief M of W. Okay, so that's what we have. And probability of EM plus 1 given W we carry over as it is. There are these two terms over here, right? The numerator and the denominator. So notice that they don't actually depend on W. Okay, so they can be thought of as sort of normalizing constant. Normalizing why? Because we know that if we do this basically this same thing for each W, right? There's a whole set of W's and we want to have a belief ascribed to each of them. Belief n plus 1 needs to be a probability distribution, right? If you sum up the beliefs over all W's, that's got to be 1. So rather than really bothering to try and find out what these two terms are, right? We can just make the claim that belief m plus 1 is a probability distribution, and therefore if we just take these two terms which we have, right, which depend on W, but calculate those same terms for every possible W and sum them up and put that in the denominator, then belief m plus 1 needs that in order to be a probability distribution, right? Because if you sum up now this thing over all W, then the numerator will be basically the denominator, it will become 1. If you don't have this in this form, then it won't sum to 1. So, I mean, this is like a standard thing to normalize without really bothering about these event probabilities. Okay, but here, right, we have it. Sometimes this result, right, is, in fact, sometimes the fact that we do this normalization is not really very significant. Some people might simply say that belief at m plus 1 is proportional to belief at m times probability of E m plus 1 given W. And what those people are saying, in other words, is sometimes rephrased as the posterior, okay, that is belief of m plus 1, is proportional to the prior, okay, that is belief at m times the likelihood, right? What is the probability that this particular W generated the evidence that we last saw? So that likelihood gets multiplied by the prior probability of W to give up to normalization the posterior probability of W. Good. Okay, so this was like a standalone, I think, sub-module lecture in itself, but this is basically Thomson sampling. Okay, so how does Thomson sampling correspond with doing Bayesian inference? See, what we don't know when we are interacting with a bandit is the bandit instance, right? So technically speaking, the worlds which are unknown to us are the set of bandit instances, but we additionally have the facility which is convenient that the world is actually decomposed into n arms, right? So you can actually just do this one arm at a time. Okay, so let's just look at each arm A and say that there is a true mean of this arm PA, which we don't know. So we will keep a belief distribution over the true means, right? Literally those PAs are the same thing as our worlds W, and we will refine our belief distribution over these worlds as we get evidence. Evidence here is the 0 and 1 rewards. Okay, so normally you start by having like a uniform prior, okay, from 0 to 1, but this is not necessary. Okay, if for whatever reason you have additional knowledge, you think the means are going to be small, right, close to 0.05 or something like that, you can have like a different belief distribution with which you start. Okay, but just the uniform distribution is most commonly used. But the job that we need to do, right, according to the principle of Bayesian inference, is every time we get evidence, we must update our belief distribution. So let's see in the context of Thompson sampling and Bernoulli samples how that happens, right? So we have our belief distribution at time m, and let's say that from this particular arm we got a 1 reward, right? The evidence that we got em plus 1 is a reward of 1, also known as a success. Well, according to the update rule on the previous slide, we should therefore set belief m plus 1 of x, right? X is actually going over 0 to 1. It's the variable that is standing in place for our unknown true mean. Belief that the true mean is x, right, should be the prior, which is belief at time m of the same thing, times the likelihood, right? So why are we multiplying here by x? Well, if x is the true mean, right, the probability that it generated a 1 is x. Okay, so the likelihood in this case is x itself. All right, so that's what we set it to be, and of course we integrate out the numerator for y going from 0 to 1 to make sure that belief at n plus 1 is also a probability distribution. I mean, this is what we should be doing. And similarly, if we get a 0 reward, we should basically do the same thing, except the likelihood is not x, it is 1 minus x. If x is the mean, the probability of getting a 0 is 1 minus x, right? So you should do this sort of an update. Well, I just said you should do this sort of update, but lo and behold, this is precisely what is happening if we use this beta distribution with the number of successes plus 1 and the number of failures plus 1 as our belief distribution. Okay, so you can look up Wikipedia for the actual definition of beta PDF, right, of x, right, and see that if you take that and then multiply by 1 minus x and do an integration in the denominator, what you'll actually get is the beta PDF of the beta PDF with one extra failure. Okay, if you had gotten a failure here and one extra success, if you got a success over here. Okay, so take some time out, right, to see that if we substitute belief m of x is beta of s plus 1 f plus 1 of x dx, okay, then this is exactly satisfied. Okay, and this is also exactly satisfied. It will be. All right. By the way, I mean, on the previous slide, I think I used a sum in the denominator. Here I'm using a integral. That depends on whether you have like a discrete variable or a continuous variable and you need to integrate. Okay, but the principle is basically the same. Okay, so